When I say the word real planes or complex planes, you probably think about something like this, or maybe even like this. But do you know what mathematicians think about when they hear the same thing? Yes, that's right. Now, the last time we were discussing the real plane, we learned how to convert it into a complex plane. And well, there was nothing really plain about it, was there? We had real numbers on the x-axis and imaginary numbers on the y-axis, the whole deal. But thanks to this complex plane, we are able to directly plot any complex number. And you know what? The figure representing one or more complex numbers on the complex plane is called an Argand diagram. Now, do you see these straight lines connecting the points to the origin? Such a distance from the origin to any point on the plane is called the modulus of complex number, the motive of this lesson. Like this one, from origin O to a complex number A, it is the modulus 2. But what is its value? Well, to obtain its mathematical value, we only need a one-time effort. Let the length OM be x and MA be y. And since we know that MA is perpendicular to OM, therefore, by simply joining O to A, we will get a right angled triangle OMA. And now, the required distance OA can be found out by the Pythagoras theorem. Simple. By substituting the values and simplifying it a little, we get the modulus as you can see. And if we represent our complex numbers with z, then this is the general formula to find the modulus, where x and y can be substituted from the real and imaginary part of any given complex equation, or from the xy coordinates in case you are working with an ordered pair. Now, I'm sure you noticed the absolute value brackets. Once again, telling us that the value of modulus must always be positive, since it is the length and we know it cannot be negative. How about using this formula right now to find some moduli? Starting with the first complex number, let it be equal to z. Next, convert it into the standard form by moving the minus sign inside the bracket. Good job! By comparison, we can see x is 1 while y is negative root 3. Let's plug the values into the formula and our answer is 2. Simple, right? Let's try another one. This is just a real number, but no worries. That just means its imaginary bit is 0. And if you put it in the formula, you'll find that its modulus is the same number again. No problem. But what about this complex number with no real part? It's still a complex number, so we will represent it by z. Then you know what to do. Plug it into the formula. Notice the answer is once again just the imaginary coefficient itself, but the positive version. And that makes total sense. That was a great effort. Now, let's try one last example. This complex number has both real and imaginary parts. But you must be an expert on getting the modulus by now. So, simply recall the formula once again and solve for the answer. That was incredibly easy, am I right? You were plain awesome! Now, in our next video, we will look at some theorems related to complex numbers and their modulus. But nothing to worry about. This level of ease will only continue.